So I work on the Rebuild project pretty much full-time. So it's the project Tim McKay's leading in the physics department. We're interested in looking at reforming and improving STEM education and just asking basic questions about it. In 4 departments right now, but probably expanding beyond the 4 departments of biology, chemistry, math, and physics in LS&A. My role in that is to bring data to specifically be the interface of the data warehouse to start to inform and use this angle on asking these questions about how to teach STEM classes better. So what I'm going to talk about today, so in the course of doing all this, a lot of side projects come up, and one of them that we've been interested in is possibly advising students or using the information we have in the data warehouse, specifically grades, maybe to advise students better, or maybe to help faculty. Like the outcome of the Rebuild project would be to improve STEM teaching. So an outline of what I'm going to talk about today. So why is prediction interesting at all? I'm going to talk about just an example from Physics 140. I will say, so forgot to mention the title of this talk, I think, was Multi-Institutional Grade Penalties, which we submitted back in December. Since then, a lot has happened. Becky Matz from Michigan State University is going to come and talk about that, I think, in a little more detail in a couple weeks. So I moved some of that material to Becky, and I'm going to spend some more time talking about this grade-based prediction, hence the title. Yeah, so why is prediction useful at the university? I'm just going to use a quick example of Physics 140, so how prediction sort of works out in a particular class. I'm going to talk a little bit about some of the work we started trying to test if some of the trends we see replicate outside the University of Michigan. So some of the things we see them elsewhere, and if we don't, can we learn from those places that we don't see them? Then I'm going to show some of the different models that we've started to work on and build as a means to prediction, and then just some quick conclusions. So prediction in general, so why is it interesting? Well, advising, of course, so we want to meet students' needs and expectations. So, student comes to you and they're going to take a class, so they want to decide on a major. Yes, grades, we're going to talk a lot about grades today. Grades aren't the whole story, but grades are abundant, and they're something that we can use to help the student decide if grades are important to them. Here's maybe what they can expect to do in this particular course or in this particular major. A lot of what we've been doing in Rebuild has been using grades and using prediction to identify irregularities. So that's kind of where the grade penalty work that you've probably heard so much about comes from. So, we've used GPA, grade point average, as sort of a predictor for how you're going to do in a class, right? And we compare students' grades that they actually got to what we would expect from a grade point average and identify differences, right? So those sort of irregularities and outliers form another sort of research topic. Something we hope to do more, I think, in Rebuild, and we're working on now, is so we have a baseline, a prediction that we can use that we build from any of these models. Can we use it to test a treatment, right? We'll call it a treatment. You do something different in the class this term. Did the thing you did have an effect, right? So having a solid prediction or a solid baseline is one way to assess whether you've made a difference. And so again, grades are one metric of performance. Of course, they're not the only metric. There are lots of things, lots of different predictors we have, I'll just say along the way. So, of course, we're going to talk about grades. There's this grade-based GPA, which I just talked about, and then Tim's work, which you're all well aware of. Becky Matz is going to talk more in detail, as I already said, about interinstitutional comparisons of grade penalties. But that's grade-based. You can also use demographics and high school information as a predictor for, how you're going to do in a class, how you might do in a major. Different kinds of exams, so standardized exams, diagnostic tests, placement tests, those kind of things. And then I guess what I'd call validated instruments. So I think instruments is a word I always think of, instrument, are you going to build an infrared detector? I guess that's validated instruments is something that I've become familiar with in reading more of the social science literature, which is, I guess I would liken it to a survey. So you go and ask somebody some questions, and you try to understand how's their attitude, or how do they feel about chemistry, right? How do they feel as a learner in chemistry, for instance? It's something I hope to learn more about, certainly. So why grades? Well, first of all, I'll point you to some literature. There's a lot out there written about grades. A couple things that caught my eye there's a recent review by Shinsky and Tanner. So this is in this journal CBE Life Sciences Education. It's a really nice overview of grades. So ever since evaluations were first used regularly at universities back in like the 17th century. It starts from there and it goes all the way up to the current day to talk about grade inflation. There's this well-known paper written by Max Meyer. I believe he's an experimental psychologist in Science in 1908. I'm sure many of you have seen this quote before, where they introduced the letter grade scale at the University of Missouri in 1908. Professor Meyer went in and looked at it in detail and concluded that the result of the investigation, this is letter grades, is that the experiment started by the faculty 5 years ago at the University of Missouri must be pronounced a complete failure, right? So part of my purpose here is to introduce grades and to knock them down and say how horrible they are, but then I'm going to go ahead and use them anyways. And finally, another interesting paper is this written by Sasha Akin and Paul Courant in the Journal of Economic Perspectives, and it just talks about some of the gaming and some of the incentives that grades produce, right? So incentives for students and incentives for faculty to use and apply grades. That's a really well-written paper, I think. So, as I've pointed out, they're flawed, but they're still informative. So people put a lot of effort, professors and faculty put a lot of effort into setting out their grades, and they're recorded meticulously in the data warehouse. So we have them going back. It's a little bit sparse, but going back as far as I've seen as 1974. So before I get into too much analysis, this is kind of a 30,000-foot view of grades at Michigan. So there's a lot of information on the slide, of course. You see up here on each column, so this is a single figure, so the left column should sit on top of the right column if we had a screen that went down to here. So on the right column here, on the side of each of these is a department at the University of Michigan. Going across the top then, from 1 to 10, are the top 10 most taken, highest enrollment courses in those departments. Okay? So there are 10 going across. 1 over here is the highest enrollment. 10 is the 10th highest enrollment in that department. So I'll just zoom in here. This is a zoom in of just 2 particular departments, just so you can see in a little bit more detail, because I don't know if you can read everything. But what I've written on each of the boxes is an actual course number. So the coloring then on the boxes is the average grade given in that class, in that particular course, right? So yellow, it ranges as high as, I think, light yellow and white is 3.85, all the way down to dark red, which is about 2.65, right? So departments with lots of red are giving out lower grades in general. Departments with lots of yellow and white are giving out higher grades in general, okay? So I've just zoomed in on a couple departments here. So I've color-coded the departments according to whether I classified them as science, social science, humanities, or other. So science includes things like physics and also engineering. So then down here we can just see as an example, I just pulled at random Germanic languages and literature, the 10 courses by enrollment that department teaches, top 10, mostly yellow, right, going all the way over to 386. Here's electrical engineering and computer science. This is down towards on the right side, down towards the bottom. They give out lower grades generally, right? Yeah.
Do you have any data on how this correlates with the acceptance rate of each department?
I don't, but one example that I don't think made it on here is that we have a Department of Organizational Studies. So yeah, to actually get in the department and take courses there, you have to pass, presumably a GPA threshold or something, right? And after that point, the grades they give out are higher. So I know there are departments like that, but as far as acceptance, I can't see much.
There's only a few that have that kind of admission into a department. So for the most part, students self-select into these in whatever way they do.
Any other questions about that? A lot of information there. Okay, so one of the important things is, grades. grades are different among the different departments. I guess that's no surprise, right? But using things like grade points and grade point averages and just collapsing the grades together is sort of averaging over a lot of information, throwing away some information about students and departments that we might otherwise use. Let's see here. There we go. So an example then of how we've been using grades to identify irregularities, but this is more aimed at showing how it can be a predictor. So you've all seen this plot, these sort of plots before. I think Tim's shown them. So this is for Physics 140. On the bottom axis is the GPA and other classes. So you took physics this term. We look at your GPA, your GPA up to and including this term with Physics 140 removed. Okay, so it's almost like your grade point average, but not exactly. So that forms a predictor, right? So your GPA in other classes predicts what grade you should get in this class. So we actually plotted the grade, then the vertical axis that the students actually got. So we binned by GPA, and then we computed a mean grade for students in each of those bins, right? And in this particular plot then, so you'll see the line going, the diagonal line here's the one-to-one line. So if there were no grade penalties, we've been calling it, all these points would scatter about that diagonal line. But as we well know, there is a grade penalty in Physics 140, meaning that students typically get grades about half a letter grade or 4/10 of a letter grade worse than one would expect from their GPA, right? So that's one sort of prediction. Put some other statistics up here where we just aggregate overall that instead of binning the GPA, we just aggregate over all the males and all the females. And you can see that the male grade penalty is minus 0.3, the female grade penalty is minus 0.5, 0.6, meaning that females experience larger grade penalty in Physics 140 than males, which is something we know about. And then for those that are interested, I've also put Cohen's D statistic up there. I know that's important to social scientists, but that's telling us something about how many standard deviations or how large the effect size is between males and females, right? So it's comparing those. So it's saying something like the difference between males and females is 0.3 letter grades. The effect size is about half a standard deviation or so.
And your N is massive. Is this over a series of years?
Yes, this is since 2002, I think. Yep. So yeah, the N up there is 23,000. So I was just using grades. So one of the things I did when I started working on this was to dig into the data warehouse and see what else there is and what else we might use to predict, right? So we've already looked at that slide with different predictors we might use. So GPA, this is just a simple linear regression. So we said, let's take a linear combination of all these variables and ask if they predict a grade in Physics 140, right? So just a basic linear regression. So at the top is GPAO. So you look at the columns over here. These are the different variables that we can regress on. Going across, there's the estimate, which is like the effect size. So in letter grades, how much this particular variable affects the grade. And all the way over at the right is the p-value, right? So is this effect significant or not? So the different, all the assumptions we violated in doing a linear regression notwithstanding, you can see there are some things where there are effects that are, non-zero, that are non-negligible. So of course the GPA in other classes, yeah, we already knew that GPA was a good predictor of how you're going to do. This regression kind of compares it to the other effects in some sense. So males, whether you're male or female, the males typically got, according to this at least, about 0.2 letter grades larger after we've corrected for all the other effects. Total taken GPA, that's just the number of credits you had, right? So this is saying if you're someone that had 50 credits, we'd multiply that minus 0.002 by 50 credits, and we get out about the number of letter grade effect you'd experience. You can see it's a little bit negative, slightly significant, meaning that if you're a senior, you do a little bit worse than if you're a freshman, right? So, right, we can keep piling all these variables and do a linear regression just to get an idea, just to get some evidence about what other effects, what other things we might want to consider when we start looking at prediction, and also looking at the irregularities we see. Okay. And then finally, I won't talk about this too much, but we found Ben Hansen in the statistics department has this nice code in R called Optimatch, where you can actually go in and you can take two sets of students, and you can go in and match and say, okay, I want to compare males and females, but I want to compare males that have the same ACT score from the same college with the same number of credits to females that have those characteristics. So instead of doing a linear regression, we can make a nice match set like this. And then what I did here is I just compared the mean grades of those matched males to the mean grades of those matched females, right? Doesn't tell us anything new, right? So the mean grade of the males is 2.8, the mean grade of the females is 2.5. So about 0.3 of a letter grade different.
And Ben,
Yep.
sorry, did you use, when you were doing the matching,
Yeah.
did you look at their other class schedule?
No,
Uh,
no, none of that went in. So the only way that would figure into this, I think, is so I made sure they're in the same college. So at least there's a little bit of that going on. Right. So I'll talk quickly about, do these predictors replicate elsewhere? So, we found, of course, grade penalty. One of the things that really started this work looking at other institutions was the grade penalty work, right? So we saw this difference between males and females in the grade penalty they experienced in physics. And we wanted to know, okay, does this happen elsewhere, or is this just particular to Michigan? So we started this project among the institutions of the CIC, which is basically the Big Ten plus Chicago. I think we ended up with 10 institutions that actually participated at some level. To come together and say, okay, hey, let's pull the same data on all of our students, standardize it in a table, and then run the same code on those tables. So at least we know we're doing the same analysis, right, across all the different institutions. Yeah, the students at these places and the institutions themselves are way different, as we found. So, that was the basic idea, was to go in and do at least control for that source of variance. So what we did is we standardized the student data, so we had a lot of phone calls, me with other research scientists, with data administrators, with other kinds of administrators that all had different expectations about how this should go. A lot of awkward silences. A lot of worry about privacy, right? So understandable, right? They don't want to ship their data to us. Okay, that's fine. So that's one of the reasons we standardized the tables like we did. So this is an example up here of what we call the student record table. I don't know if you can see it too well, but for each institution, they had to build a student record of all their students since 2005, creating an ID, a gender, an ethnicity, which we use this IPED specification. So that at least there's a 1 through 9 for each ethnicity of the students at each university. The first term they came in, the degree that they got the term they got a degree, transfer, things about their major and what they declared. We use zip code specifications there just to standardize things. And then their Pell status, so whether or not they're Pell eligible. So we were successful, I think, in doing a lot of there are a lot of things that we wanted to do with this. So not just look at grade penalties, but look at persistence from start to finish. So you wanted to get a STEM degree, did you persist and actually get a STEM degree? That stuff isn't as mature, it's moving along, but the grade penalties, the view of grade penalties did bear some fruit. And as I'll point again to Becky Matz. One of the things, like I said, that we did discover along the way is, and it's not too surprising, is that despite our efforts to standardize everything, the institutions are so different. So one of the things that really tripped us up were, Ohio State switched from a semester system to a quarter system, or from a quarter system to a semester system. Okay, how are we going to code that? How are we going to make everyone happy there? There are places that you declare upon admission when you get into college, and then you persist or you don't. Michigan, you don't have to do that. Presumably you can do it up until your last day, declare, right, and then get a degree. So answering those questions, the first thing we have to do is just to be transparent. So that's an ongoing project. I think it is bearing fruit, and I'm not going to talk a lot about it, like I said again, because Becky's going to hit it. So how far can we go with grades to predict? Well, the GPA is what I'm going to call our baseline sort of grade predictor, right? So we've already shown what we can do with that in terms of grade penalties. So what's GPA? Well, it's a credit hour weighted mean of your grades, right? As we saw before, it's agnostic to subject, right? So there are these subjects where they give out a lot higher grades, and there are subjects that give out lots of lower grades. GPA doesn't care about that, right? It just takes wherever that grade is, wherever it came from, and averages it. A second estimator is to try to start to account for places that are subjects that are handing out higher grades or lower grades, right? So if we just compare you look at the distribution of grades in a particular class, and we compare you to the mean of that class, we can make a ranking for you and say, okay, well, you were 2 standard deviations or you were 2 letter grades above the mean, right? And we don't care whether they're handing out C's on average or whether they're handing out B's on average, right? So you can create a credit hour weighted average of that and say, okay, well, that's going to be a predictor. Finally, what you can do is you can say, well, the students that I'm in this class with, I don't know what kind of quality students they are. So they typically get low grades or high grades, or how do they perform in school? Well, we can build a full-fledged linear regression with all the students and all the courses they ever took, and build this coupling in, right? Such that we know we have some indication of how the students that we're being compared against did in their other classes, right? So just to give you another view of this, is students are taking lots of other courses against one another, right, with one another, and they're being compared to other students and getting grades. So this is a network plot just showing each of the nodes here is a course. I don't know if you can read the courses very well. These are high enrollment courses. Each edge then is a number of courses, the number of times that 2 courses were co-taken by a student, right? So just highlight a few things here. So this cluster here, if you can read any of those, there's Math 115, there's a Chem 130, Stats 250, Bio 171. So these are all sciences, right? So all the science students are taking lots of classes with each other. And there are subclusters in here of people that are biomed and pre-med, so all the biology and the physics for, I guess we call it physics for pre-meds is in there. And then the engineering cluster down here. So there's lots of upper level math in there, and physics 140, physics 240. Engineering 100. Over here, there are some other clusters of students that are taking econ. This is the econ and business cluster. There's another psych cluster down here. A lot of people taking psych classes together. And up here at the top, then there's this course. I think it's Cultural Anthropology 101. Doesn't mean that a student that took Cultural Anthropology 101 never took a course with any of these other students. It just says typically they didn't. Right? It's just kind of an average statement. So part of the point is that students are being compared differently, regardless of how we try to do this. Students are being compared against different students depending on what their career was, right? Depending on whether they were a science major or they were an English major or whatever they were. So we want to use that. We want to use that information in this model, right? So this is the point of this what we think this student fixed effect model, I'll call it, is going to do for us. So what we do is we simply, like I said before, each grade at the university is a combination of a student fixed effect and a course fixed effect, right? So the course fixed effect is something like the mean grade that course typically gives out. Not precisely, but I'll say something like the student fixed effect is a number that's centered on 0 with a distribution, right? So typically an average student will go in, means an average student will go into this class and they'll get about the average grade, right? And then the student fixed effect is some number. If you're less than 0, you get a little bit less than the average grade. If you're greater than 0, you get a greater than average grade. So it's not precisely what's going on here, but it's a rough approximation. In practice, to solve for these student fixed effects and course fixed effects, such that all this coupling is built in, we have this giant matrix of 6,000 grades and 150,000 student course effects. It's a linear regression model. That's a matrix that's really hard to invert. So we found this model, this well-known economics of education researcher. His name is, I don't remember his first name is, R.C. Diacono, I think you say his name, but he's at Duke. Has a nice method for inverting a sparse matrix like this. So fortunately, this matrix is sparse. We aren't going into great detail about cause and effect with any of these. So all I care about at this point is whether this matrix that we invert in this method that we use to get a better predictor predicts better, right? So what did we do then to ask which of these predicts better? So we just took these. There are actually 4 different models. I'm just talking about 3 up here. So we ran our different models. This GPA-R1, grades above replacement 1, student fixed effect. We ran this and all the data up to fall 2013, and then we asked in winter 2014, let's predict what the grades will be for those students in winter 2014. So there are of order 150,000 grades, I think, in winter 2014. We took our prediction. So say our prediction is for GPA for each of those students is just they're going to get in this course what their GPA is. So we basically make a big scatter plot and we compute the Pearson correlation coefficient of that prediction, right? So for GPA, Pearson correlation coefficient is 0.4. For the student fixed effect, the Pearson correlation coefficient is 0.7. Right, so we would call that a win on a global scale, right? So we've just looked at all the grades and said, okay, on average, we do way better with our best model. So we call that a win. When we go in and look at the details of what's going on at an individual course, this is Chem, I think Chem 130 from winter 2014. So on the top plot there's cumulative GPA, and the bottom axis is grade. So there are 500 or 600 students, I think, in Chem 130 this term, right? There's a dot for each one of those students, a dot for the grade they got, and a dot for their cumulative GPA at that point, right? You can see it kind of goes from left to right, a lot of scatter. When we go in to do the same thing now, grade on that axis for those few hundred students, and the student fixed effect on that axis, you can see that the scatter gets smaller, right? There's a little bit more tilt to that relation, and you can see that from the correlation coefficients then that the correlation with our fixed effect model is better for that class, right? So in detail, you'd say, okay, well that correlation coefficient we saw on the global scale makes sense when we start to drill down and look at individual courses, right? So we can do the same thing for those two models again. So this is for the GPA on the top, the student fixed effect on the bottom. This is for Chem 210. You look at the correlation coefficient, it's 0.55 for Chem 210 and 0.69 for the student fixed effect. So we would say, okay, that makes sense. Now when we get to the upper level courses, right, there are way fewer students taking these courses. So this is Chem 463. Again, the same two fields, cumulative GPA on the top and student fixed effect on the bottom. The correlation coefficients aren't all that different. I haven't done any tests here to ask, is this correlation coefficient significantly different from this one? But the point is that the statistics get a little bit worse. So sort of any predictor you use at this point starts to get noisy, right? And it's hard to tell whether your predictor is really doing any better, any differently than the cumulative say the cumulative GPA. So we can go in and start to tabulate this for a few courses. I won't talk about each one of these. See how much time I have. So the chemistry you already saw. I guess it's the fourth set of courses there. 130, 210, 463. There's psych up here, a couple psych classes. English down here in the bottom. So a couple of things start to jump out, I think. And it's not uniform. We're still picking this apart. It's not a uniform conclusion across all courses. But we typically, I would argue, predict better in courses where the enrollments are higher, right? And especially, so Chem 130, Psych 111, the student fixed effect does better than the GPA, right? And it's because it's using this, there are many more comparisons to do between students in courses, in places where they're taking the courses a lot, right? So these get weighted, in our model they get weighted more, okay? The lower enrollment courses, the higher level courses, of course there's a statistical problem there, but there's also a difference in how departments use grades. So we saw remember the original colorful plot I put up there before about the different ways departments hand out grades. There's that issue, and so if English, I'm looking at English here, if English typically, if they give out narrower grade distribution, say they give out a lot of C's, and it's not a wide grade distribution, or everybody gets an A, there's not much information in that grade, right? So it doesn't matter what predictor you use of these three that we put up there, there's just no information being given there, right? So you might look at that and say, well, you know what, for upper level, let's say for upper level English classes, I don't want to use a GPA. I don't want to use anything to do with grades. I want to use something else. I don't know what the something else would be. But the point is that any of these models that we use, there needs to be more intelligence behind it. So we can't just take it and say, okay, this is how you're going to do. And I don't think that's a surprise to anybody. So to conclude then, the grades, one of the things we found, I think we've kind of beaten the dead horse, is that the grades predict other grades well, right? It's not too much of a surprise. The student and course relationships, so which students are taking courses with which other students, allows us to do a little bit better if we want to use grades to predict how students are going to do down the road, right? So using that extra information in the network of students is a win for us. One of the things that I've been interested in, at least, is advising students. So if we want to use any of these metrics, whether it's GPA or the student fixed effective, I advise students to give them an idea of how you're going to do, how we think you might do in this class, or how you might do in this major. You still have to ask, okay, which metrics are we going to use, and which students are they going to be for, and in what context is it going to be? So, again, that may not be news to everybody, but I started from the high level to say, like, we can come in and do this right, and take the fanciest model we can come up with, and it'll work for everybody, right? That's just kind of the ground level null hypothesis. Not true, not surprising. Yeah, and I mean, I'm not going to say surprised, but all this talk about grades that they put up here, it's always such a hot button topic, right? And people like to jump on grades and tackle grades. But using any of these methods that involve grades just gives you, pause and to take a second to reconsider why do we use grades anyways? Who wants the grades, and why do we, and what does it mean the GPA and the grades that the student carries with them from the university, right? So that's, I don't know how that's a bigger fish to catch. And that's all that I had. Thanks for listening.